Okay, we continue our morning session, and our next speaker is Professor Haibao Duan from Chinese Academy of Science, and he'll talk about making Schubert calculus calculable. Please.
Oh, thank you very much. Thank you. Yeah, it's really a great pleasure to have this wonderful opportunity to communicate with colleagues and friends. Yeah, after 3 years, long time. In particular, on the occasion to honor, Victor Buchstaber's 80th birthday. So the title of my talk is "Make Schubert calculus calculable." In the 1900s, Hilbert proposed a list of 23 problems. The 15th one is focused on the enumerative geometry of 19th century, with the title "Rigorous Foundation of Schubert's Enumerative Calculus." So centered around this problem, my talk will be given in 4 parts. The first part, I'll give you a very brief introduction to intersection theory. Fortunately, all the audience are from algebraic topology here. And the next is a background of problem 15. In section 3, we will recall some fundamental contribution of Waerden, Eisman, Andre Weil, and also Bernstein-Gelfand to Schubert calculus. Because of their work, the fundamental problem of enumerative geometry will be made precise, which is Schubert problem of characteristics. And in the final part, I will talk about joint work with a colleague of mine called Xue Zhao. Will give a solution to the problem of characteristics, both theoretical and computational. So let me start with the introduction part. In 300 BC, Apollonius has a paper called tangency. In this paper, he proved the following theorem. The number of circles tangent to 3 given circles in the plane is 8. As you can see in the picture that in the plane, there are 3 black circles, which generically black circles. At the same time, there are also 8 pink ones. Each pink one has the property that it tangents 3 of the black ones. The original manuscript of Apollonius was lost. People get to know this result from a report by Pabst dated in the 4th century. During the Renaissance, different proof of the result were founded by several people, including Volta, Riemann, and Newton. I have referred the cover page story about second course in algebraic topology. There is a title called 3264, which means given 5 conics in the plane CP2, then the number of conics tangent to them is this number. Isaacs' discovery on Euclidean coordinate makes it possible for geometers such as Maclaurin, Euler, Bezout to use polynomial system to describe the geometric figures that satisfy a system of geometric conditions. Consequently, many problems of enumerative geometry have the following purely algebraic formulation. Given a polynomial system, in this polynomial system, you have the number of equations equal to the number of variables. Then find the number of solutions to the system. We know the answer for the very special case n equal to 1. The result was called the fundamental theorem of algebra which says that if you have a single equation, then the number of solutions to this single equation is the degree of that polynomial. The study of fundamental problem of algebra then motivates intersection theory. The general statement is the following one. Given a set of subvarieties in a smooth projective variety M that satisfies the dimension constraint, that means the sum of the dimension of the subvariety equal to k-1 times the dimension of the whole space, where k is the number of these subvarieties. Then the problem asks, find the number of intersection points of these subvarieties in M. Yeah, the connection between this one and the previous one is quite obvious, because by homogenization, each equation gives rise to a polynomial on the n-dimensional projective space. Then its zero logs gives you a hyperplane. Then the intersection of this hyperplane that tells you the number of this equation. The hyperplane could be subvarieties. Just for the purpose of solving intersection theory problem, Leibniz in 1926 developed cohomology theory. Previously, Poincaré invented homology theory around 1900, but until 1926, Leibniz feels it's necessary to introduce cohomology theory in order to study the intersection theory. Then, in terms of the framework of Leibniz, the statement could be the following one. Assume as before, we have a set of k subvarieties in a smooth projective manifold that satisfies the dimension constraint. Then we let alpha I to be the Poincaré del of the circle class or the fundamental class of the subvariety. Then the problem is translated into the following form. Compute the conic period. We take cup product of these cocycles, then evaluate it at the fundamental class of M. We get a number, which by Durham theory is equivalent to take the integration along M of the alpha exterior product with alpha k, because in Durham theory, we know that each alpha I can be represented by a differential form. Cup means the cup product. So rather quickly, we have introduced 3 different versions or different approaches to problem of enumerative geometry. Let me temporarily leave one problem here. Which one is mostly calculable? So let me turn to the second part of my talk, which is the background of problem 15. In 1879, Schubert published a book called Calculus of Enumerative Geometry that represents the summit of intersection theory in the 19th century. In the course of developing intersection theory, he also applied this general theory to find many, I could say, amazing applications to enumerative geometry, at least just for 3 examples. For example, the first one says that the number of conic tangent to 8 quadric in space is 4407296. The second one is the number of quadric tangent to non-quadric in space is 666841088. Here the space means 3-dimensional projective space. Yeah, this result were very much amazing, but Schubert's work was also controversial at his time, because in his work, he made extensively use of Poncelet's principle of continuity, which was already criticized by Cauchy early in 1816. To avoid people's criticism, Schubert has renamed this principle as the principle of special position and the principle of conservation of numbers twice. But soon after, people realized these three principles are basically the same. The most precise criticism comes from Van Waerden. He commented that Schubert's exposition was so sketchy that gives no definition of intersection multiplicity, no way to find it, nor to calculate it. Yeah, I add a remark here. Nowadays, the three principle has been justified in topology as the homotopy invariance of intersection numbers in topology, and in algebraic geometry as a truth moving lemma. These are no common knowledge. So in 1900, Hilbert asked to make a rigorous calculus, make Schubert's calculus rigorous. Yeah, it's quite interesting to see the second part of Schubert's problem. He apparently feel it's quite interesting that Schubert was able to get those geometric numbers without solving any algebraic equation. So he could say Schubert could be able to foresee the final degree of the system before carrying out the process of elimination. So let me go to the third part of the problem, the earlier contributions by great many mathematicians. So get into the central part of Schubert's calculation. I directly take two tables of computation from his book. Yeah, this book consists of equalities which evaluate a monomial by an integer. Yeah, there is a common, for example, in the first table, he used the monomial mu in mu nu lu to denote the number of conics that pass through given point, intersect m lines, and tangent to n given planes in the space CP3. This equality was called by Schubert himself as characteristics, and also called Schubert's symbolic equation by earlier researchers. Schubert claimed in many of his works that the problem of characteristics is the fundamental one of the whole enumerative geometry, but it took 60 years for mathematicians to make this problem precise. Below, I'll give a brief account to this story. The study of problem 15 began with the Italian school. Two representing work of the school were due to Seville. These are Italians. The first one is the principle of conservation of numbers, which we have explained before. It's the homotopy invariance of intersection numbers. So this has been secured. The second paper is in English. It says that the foundation of enumerative geometry under the theory of characteristics. Van der Waerden commented that the Italians erected an admirable structure, but their logical foundation was shaky. The notion were not well defined, and the proof were insufficient. This is a photo where the Italians has a debate on intersection theory. The one on the desk is severe. Yeah, it's remarkable that Van der Waerden, at age somehow 26, he was the first one who proposed to study problem 15 in the context or in the framework of cohomology theory just developed by Lefschetz in 1926. He had the following crucial observation that enlightened the later course on the study of problem 15. The first one says that he said that each Schubert symbolic equation is nothing special but a homological relation in some projective manifold. The second one is also very basic. He says that the solvability of a characteristic problem depends on a finite basis of the cohomology of the relevant projective manifold. As we all know that for every finite dimensional manifold, the cohomology is always finitely generated as an abelian group. So there must be a basis. And so Van der Waerden asked, if one can specify a basis, then probably the characteristic problem will be solved. And finally, the aim of all enumerative methods is to compute the product in the cohomology ring of the relevant projective manifold. The next important step goes to Waerden. He has two important discoveries. The first one says that the parameter space of the geometric figures concerned by Schubert, or the moderate space of the geometric figures, are essentially certain cases of flag manifold of Lie group G. Within a Lie group G, you can have a so-called parabolic subgroup, which is the centralizer of one parameter subgroup of this inside G. If we module this parabolic subgroup, then this is a very good manifold. It's a smooth projective manifold instead of a homogeneous space. And also in the very special case, the Grassmannians of K-planes on the n-dimensional complex vector space, the set of Schubert symbols forms exactly a basis of the cohomology ring. This is also a fundamental result nowadays, both in the theory of characteristic class and also in algebraic geometry. I think every textbook in algebraic geometry talk about the secondary result. Also in Waerden's the same paper, he emphasized in many places that his work should be related to the problem of characteristics. This paper is in France. Extending the work of Waerden, Charlet, Bernstein, Gelfand, and Gelfand obtained the basis theorem of Schubert calculus in general. It says that for any flag manifold, the set of Schubert symbols forms exactly the basis of the cohomology. Here, W of G denotes the Weil group of the Lie group G. Yeah, for topologists, the proof can be given in one sentence. A flag manifold has a decomposition into Schubert cells, and each cell has even dimensional, which means the chain complex defines the cohomology collapse to the homology. So the Schubert cells directly, the Poincaré deal of the Schubert cells could give you a basis of the cohomology. Here, L is the Length function defined on the Weil group. Here I have listed, the two papers. One is by Schubert and Bernstein, Gelfand and Gelfand. Schubert announced the result quite earlier in 1958, but when the paper went to press, people realized his paper has a severe mistakes. Because Schubert believes that these Schubert cells are all smoothable, but actually not. This Schubert cell could be highly singular. So Schubert's paper remains for many years as an unpublished manuscript of Schubert. It was Bernstein, Gelfand, and Gelfand first gave a proof, rigorous proof of this result, published in 1973, I think, in Russian Math Survey. And Schubert's work, now after Schubert, Weil corrected the mistake in original work of Schubert, and eventually his paper got published in the 1990s, quite late. This is the sad story of this basis theorem. Now, granted with the basis theorem, the problem of characteristics now had a concise statement, which says that given any set of Schubert classes on G model P, express their product in terms of the Schubert basis linearly. Because Schubert class forms the basis of the cohomology. So if you take any monomial in Schubert basis, so their product has a unique way to be expressed as a linear combination of the basis element. And those coefficients are called Schubert's characteristics. To bring a connection of this problem with original work of Schubert, I quote a record by College in 1940. He recorded that the fundamental problem which occupies Schubert is to express the product of these symbols in terms of other linearly. It also says that Schubert succeeds in part. He could be able to perform certain computation of this. Nowadays, the characteristics has many different interpretations in geometry, algebra, topology, and representation theory, where they were called, for example, the characteristics by Schubert, which is the fundamental data to solve the enumerative geometric problem. And Hilbert calls this the degree of the final equation of a system. And for the very special case, k equal to 2, these numbers are also called the structure constants of the flag manifold by topologists, because it describes the ring structure of the cohomology of the flag manifold. These are also called Littlewood-Richardson coefficients in representation theory. In the Momentier's treatise Foundation of Algebraic Geometry, Andre Weil gave a rigorous definition for the first time in the history of the intersection number of subvarieties of a projective manifold. And he made the task of problem 50 just one sentence. He said that the classical Schubert calculus amounts to the determination of the intersection ring of all flag manifolds. Weil commented himself that his problem is the modern version taken by the classical topic, formerly known as the enumerative geometry in the last century. But we can actually show Weil's problem is equivalent to the problem of characteristics. Yes, the proof is short enough to be presented here. So let us recall that a ring is an abelian group which is furnished with a multiplication. Now, by the basis theorem, the cohomology is a free abelian group with a basis consisting of Schubert class. Therefore, the product of the ring is determined uniquely by the product among the basis element, that is, in other words, the Schubert symbols, which is handled by the problem of characteristics. So if you know the characteristics, you know the multiplication table of the basis element, the ring you understand. Conversely, if you know the ring very well, of course you know how to product the basis element. So the proof is quite straightforward. So this is the final part of my talk. Yeah. I have 20 minutes. Yeah. Yeah, summarize the previous work before 1960. There were two problem remains. For flag manifold, Schubert asked to compute the characteristic numbers of character of G model P. And we asked to determine the integral cohomology ring. Let's begin by point out some obvious difficulties around the problem. As we all know that the simply connected simple Lie groups consist of three infinite family of matrix group, which is the spanner group, symplectic group, and a special unit group, as well as 5 exceptional ones. So there are plenty of Lie groups. Next, for given Lie group G with rank n, then there are precisely 2 to the power n minus 1 parabolic subgroup P inside, which means there are plenty of flag manifold, depends on the choice of the Lie group and the parabolic subgroup. Also, for flag manifold, the number of Schubert class on that manifold is equal to the Euler characteristics. This can be directly seen from the basis theorem, which is normally very large. Here, I list some example for exceptional Lie group, where T is the maximum torus. So not to mention the number of monomials in Schubert basis involved. Yeah, just one sentence. So it's hopeless to solve the problem case by case. But on the other hand, we also have a good news. According to the fundamental contribution of Elie Gardin, the simply connected Lie groups are all classified by their Gardin matrix. Here I list the Gardin matrix for the 5 exceptional Lie groups. This matrix serves as a constant from the universe by which all flag manifold can be classified by those numerical data. So, yeah, it is natural to ask the following question. Can we compute all the characteristic numbers or construct the cohomology ring of a flag manifold merely from the Gaussian matrix of the Lie group G? Because the Gaussian matrix, all well known, it was listed in almost every textbook of Lie group theory. So in this section, let us try to realize this expectation. So let me assume that we know nothing about the Lie group, just we know the Gaussian matrix. So suppose that C is the Gaussian matrix of a compact Lie group, and assume that the Gaussian matrix has rank n, then we let our n denote the n-dimensional real vector space with a basis omega 1 to omega n. Then we can define in terms of this matrix C, n automorphism of the Euclidean group by the following formula. Sigma I, the action of sigma I on the case basis element is the basis element if this I not equal to chi. And in the case I equal to chi, I take the case rule of this Gaussian matrix to get this linear combination. I use omega chi minus that. Then the conclusion is, starting from the Gaussian matrix, we can construct the subgroup of the automorphism group of Rn, which is precisely the Weil group of the Lie group. Now, it follows that for a Weil group element size W, we can have a minimized decomposition. Minimized decomposition means that the length n is the least one. Then in terms of this decomposition, we can introduce so-called the structure matrix of W as the following upper triangular matrix whose size is m times m, equal to the length of this W, where everything on the diagonal or below the diagonal are 0. But for element up the diagonal at the ST place, we look at the Gaussian matrix IS at T place, you take that number, put a minus sign inside. So you get this a matrix here. Let me show you an example. As I have said, that the Gaussian matrix of exceptional Lie group G2 is this one, and by which we get 2 generators. And we can consider the following element of W with length 4. Then from the Gaussian matrix C, we can read the structure matrix, and U and V are given by the following form. You just take the number. Now, suppose that we have a m by m strictly upper triangular matrix. For example, the structure matrix of some Weil group element. Then we can define a linear map. I call it a triangular operator Ti associated to I as follows. It's the defines on the ring of polynomials in x to n, but with homogeneous degree n. This is a linear map. Because this is a linear map, I need only to give it a definition on the monomial basis on this group. For example, given a monomial in x1 to xn, we need only to look at the last factor. If the power of xn is 0, we simply put the value to be 0. In the case the power of xn is bigger than 0, Then we replace the last factor by a linear combination, where the coefficients come from the last row of, last column of the given matrix, and at the same time reduce the power by 1 and keep everything in the front fixed. Here, I1 is obtained from delecting the last column and last row. So this is a matrix with smaller sets. You repeat this, eventually you can get a number. So summarizing, start barely from the Gaussian matrix of the Lie group G, we have constructed the Weil group of G and a family of strictly upper triangular matrix, one-to-one correspondence to Weil group element, and also we get a family of linear maps. Now, applying the Morse theory to the canonical embedding of G model T into the Lie algebra, we can obtain the following formula. Let AW be the structure matrix of associated to the minimized decomposition of W. Then the characteristics is given by the following formula. Firstly, this is the operator, triangular operator associated to W. Then it acts on the product of n K polynomials. Each factor corresponds to UI, UI in the below in such a way. For multi-index in 1 to m, I use this bar to denote its length, and the sigma to denote its subverse of W. And the sum is over the subverse of W, which equal to omega. In that case, we put a monomial x, simply take product of this variable. This is a formula. This formula relies only on the Gaussian matrix of G and applies uniformly to all flag manifolds and to any monomial in the Schubert basis. So based on this formula, we have composed a package called characteristics in 2 works, whose function can be described as follows. The input will be the Gaussian matrix of a Lie group and a subset in 1 to n. It uses to specify a parabolic subgroup of P. The output will be all the characteristic numbers of the flag manifold. So let me take an example. This is a familiar example, which is the Grassmannian of 4 planes in non-dimensional Euclidean space. These are, of course, Chen class. The Chen class are the generators. This computation is at the top degree, because if I produce all the characters, the table will be very huge. So this corresponds to the characteristic number at the top degree. And we can also change to an exceptional Lie group E6. You can also get a similar result. Now, it's quite interesting to consider also Weil's problem. Let us recall Weil's problem asked, given a flag manifold, determine the structure of the cohomology ring of that manifold. The main result is the following one. For each flag manifold G model P, there exists a minimal system of Schubert class x1 to xn, and a minimal system of polynomials in this special Schubert class, such that the cohomology ring can be expressed as the quotient of the free polynomial ring subject to the ideal generated by this polynomial. And the proof is not short enough to be presented here. Yeah. Just a few sentences. Since a flag manifold is finite dimensional, the quotient group is finitely generated. Here I use I plus denote the subring of the cohomology. You just ignore the constant part, the zero-dimensional part, which is also a subring of the cohomology. Then module the ideal generated by decomposable element, because this product describes the ring inside the element are decomposable. So if you take the quotient, this applies actually for any topological space. If you do this construction, by the basis theorem of Schubert calculus, then there is a set of Schubert class on G model P that corresponds to a basis of the quotient group, because the quotient group is finite generated, so you can take Schubert. It happens that these elements are the generators of the cohomology of G model P. Now it follows that the inclusion then induces an antimorphism just because this construction. Then by the basis theorem of Hilbert, it says that there exists a finite set of polynomial f1 to fm such that the kernel, which is an ideal in the free polynomial ring, is generated by this element. Hilbert basis theorem says that if you have a finite generated ring, if you have an ideal in that finite generated ring, then you have finite many elements that generates the ideal. So this is a proof of the result. Now, combining the characteristics with the proof of theorem 4, we have composed a package entitled the true ring in 2 works. The function is the following. The input will be the Gardner matrix of the Lie group and a subset to specify a parabolic subgroup P. The output will be a presentation of the true ring. So let me show you some outcome of the computation. Sorry, I tried to put too many things into one page, but I take a typical example. For example, this is theorem 7 is concerned with E8 module E7, a flag manifold. If you do that construction, you will find that this manifold is 115 dimensional. But the cohomology as a ring, it has only 4 generators. And also the relations just has 4. But instead, if you consider the Schubert basis element of this one, it could be huge, and also the characteristic numbers are very huge. So I put an remark as the title. With problem presentation of the true ring of the flag manifold. The same thing happens also to complete flag manifold. Here I listed 4 of them from G2, F4, E6, and E7. All has the same property that, for example, the last one as a manifold E7 has dimension 133, but it can be easily presented as cohomology in terms of generator relation, has a very simple expression. One more application. For a compact Lie group and a closed subgroup H, the quotient space is a smooth manifold called a homogeneous space. Previously, this H can be arbitrary one, not necessarily parabolic. A classical problem is in topology from Gardin, Boyer, Bohm, and Toda, and by many people, is to express the cohomology ring of a homogeneous space by a minimal system of explicit generator and relations. For this purpose, people invented various types of spectral sequence associated, for certain fibrations associated with this homogeneous space. I just list some of them. But the calculation encounters the same difficulty when the cohomology of Lie group has torsion element. If the integral cohomology of the Lie group is torsion free, everything is simple. But for majority of Lie groups, this integral cohomology has torsion element, in particular if G is one of an exceptional Lie group. The last example shows that Schubert calculus makes the cohomology theory of homogeneous space appearing in a new light, in the sense that we can extend the calculation from flag manifold to homogeneous space. Here are three examples. Fortunately, let me explain the last one. Last one is concerned with E8, module E7. The first rule tabulate the non-zero homology group, cohomology group at every dimension. So I can ignore the zero equal to zero part. I just list the non-zero ones. Fortunately, all these groups are cyclic. The second rule, second column, sorry. The second column expresses the generator of this cyclic group in terms of Schubert class. So the Schubert class survives to more general case. And the third column lists the multiplication, the relation, between this generator, among the generator list at the second column. My time is up, so just I add one remark. Previously, I have communicated such computation with expert from data science. We have seen from theorem 2 that the problem of characteristics and weights problem are equivalent. We have a proof of that. Theoretically, these are equivalent. But from a data science perspective, they are completely two different tasks, because the passage from Gardin matrix to the characteristics, people are calling the data mining. You mine data from the Gardin matrix. And the passage from characteristics to the presentation of the ring, people in computer science call it data processing. So thank you very much for your attention.
Are there any questions, comments?
So I'd like to ask which computer mathematics systems did you use to write your papers?
Mathematica, because we have we started to make such computation quite earlier, very earlier. I think in almost 20 years, they are almost we can only access Mathematica, and we have very poor computer at that time in China. So,
Do you mean Wolfram Mathematica or some other?
Sorry.
You said you used Mathematica.
Yeah.
Yes, and is it Wolfram Mathematica or some other system?
Mathematica is your package. I couldn't understand.
Okay, thank you very much.
Mm.
And I'm sorry, were there some computational problems maybe on
Yeah,
Mhm.
there are many computational problems. Actually, our eventual goal is to get. Yeah, may I have a thing here? Yeah, I can see. I just but our goal actually is to compute the cohomology of the classifying space of Lie group. If we can do this, all the theory of characteristic class will be finished. Because nowadays we only know when G is unitary group, we have chain class. And rationally, if we consider as ON, we get the punctuation class, Steve-Whitney class. But our ultimate goal is to compute the integral cohomology of all Lie groups. There is a passage to, one of the direct passages is this one. You have such fibration. Yeah, this can be computed. And in general, for every Lie group, there is a maximum parabolic subgroup H, which looks like this. In this case, this one is also no. So the problem is if we can compute this one, and also, this is, then you could be able to get this one. This is what we try to eventually try to get there. But we have been successfully to get all the integral cohomology of Lie group. This is a problem raised by Elie Gardin in 1929. When G is one connected, we have one connected. We have a uniform method to construct this from the cohomology of this flag manifold. So in this sense, this computation are somehow partial result has not yet completed. Of course, there are many problems related to this problem because in this you have the invariant theory, you have the transgressible element or non-transgressible element. All this involves details computation, which we hope we could be able to do, but we have only two people. I and my colleague.
Thank you very much for your answer.
Maybe I also ask something. So that's very interesting. So you say usually it's like in classical approach, like that's the Allenberg-Moore spectral sequence is used to vibration to calculate the cohomology of the homogeneous space. But now you use your computer package, Schubert calculus, to calculate the cohomology of the homogeneous space. So you kind of reverse the gear, right? So you're also using some kind of spectral sequence. There's a third spectral sequence, or that when you say transgressive elements, it's in the third spectral sequence of this.
Because when H is, let me say, every Lie group has a parabolic subgroup of maximum rank, which is type IN. So this is not. This is not. So it's very much hopefully, yeah, to get here. This is, but could be a subject where I have been very keen to go there, but anyway, yeah, it's very hopeful.
Right. And also you mentioned that you can calculate in the case of the flag manifold, when G over parabolic subgroup. So
yeah,
you said you can, when G is an exceptional group, then this flag, the cohomology of the flag manifold also has lots of torsion elements, right?
Yeah.
And you can calculate them with, you can calculate, when you say you can calculate the cohomology ring, you mean including torsion elements, or because what you said also you can identify it with a Chow ring, but the Chow ring is already a field, right? But you mean the integral cohomology ring.
The computation I have shown here are all related to exceptionally group.
Yeah.
Because for the matrix group, somehow you can do introduction, but exceptionally group is too exotic. I have discussed with Mimura many years. He said the exceptionally group somehow like a monster.
Yeah.
So this is why we are trying to do this calculation.
Thank you for your talk. Thanks again to Elmer Rees who joined us.
Yeah.
But my question is such, you know that you mentioned many classical problems related with this calculation. But at the time, people don't know what does mean K-theory, cobordism theory, but you know, there was the papers where people calculate K-theory of compactly groups. First, the paper of Michael Atiyah, next, the Hodgkin paper.
Yeah.
Question, are the geometrical interpretation of A-theory of homogeneous spaces what in the term of classical?
Yeah, this is related, just what I mentioned here. Basically, a key problem is to deduce from this sequence the Weil invariance, concrete presentation of Weil invariance of that. Graham Segal's work and Atiyah's work already try to do this. I think around the 1960s or 70s, they did a lot of work trying to make this representation theory, connection representation theory with K-theory transparent, but not successful. I don't think that their work not successful. The key problem is we need to do effective calculation. This is, you just mentioned MREs. Let me just take 3 more minutes. Sorry. Yeah.
Mike, I think that's otherwise it's start.
Yeah, I have mentioned a formula here. Yeah, it was at the very start, my English not good enough. So when Elmer come to visit me at 2002, I asked him, he helped me to formulate this operator. He helped me to formulate this operator. And at the same time, he said, Schubert have a similar formula, but I don't know what's exact relationship between you and him. At that time. So we have a common friend, Elmer Rees. Both we have, colleague and we have a cooperation for many years. He always talked, every time he talked to me, Victor Schubert, his mathematical achievement and his charming personality. That's many years ago. He said you have some very similar to this operator.
Okay. Let's thank Haibao again.
Thank you very much.